Dear student, I am Dr. Harold Thomas, Professor in Applied Geology, Dr. Hari Singh, Gaur Vishwavidyalaya, Sagar. Today, I will deliver my lecture on MGO, AL2O3, SIO2, S2O and CAO, MGO, SIO2 diagrams. This topic I will cover under the following heads: introduction and the diagrams. Hope it will be useful for you. Try to be regular in course. The MGO, AL2O3, SIO2, S2O diagrams, or MASH, is regarded as a model system for peltic rocks of crustal origin. This system contains at least 4 mineral phases of petrotite, for example, phosphorite, anisotite, pyrope, and spinel. It is again of interest in discussing phase relation within the earth mantle. This is in fact very simple triangular diagram which a student can use for the silica deficient MgAl rich composition. Such a diagram is projection from the S2O corner onto the anhydrous base SiO2, AL2O3, MGO, FeO plane of tetrahedron. MGO, AL2O3, SiO2, S2O, Newton 1972. Because Fe almost invariably substitutes Mg in all phases, therefore the relevant system for the natural rock would be FeO, MGO, AL2O3, SiO2, S2O. F-mass system, Henson and Green 1971. In this system, some suitable phase relation have been plotted in FeO, MGO, AL2O3, SiO2. Robinson and Jeffy 1969 and Sharma and McRae 1981 projected the phases from sillimanite onto the SiO2, MgAl2O4, FeAl2O4 plane. See figure. A student can also project corundum or quartz as shown in figure. The ternary system, CAO, MGO, SiO2, the CMS system is almost truly ternary in natural metamorphosed siliceous dolomites with CO2 and ultramafic rocks. The diagram is straightforward. C equal to CAO, M equal to MGO and S equal to SiO2. No subtract. Let's plot the following minerals: phosphorite, Mg2, SiO4, anisotite, MgSiO3, diopside, CaMgSi2O6, calcite, CaCO3, quartz, SiO2, periclase, MGO. Calculation: phosphorite has M equal to 2, S equal to 1 and C equal to 0. Normalize that becomes M equal to 0.67, S equal to 0.33 and C equal to 0. Similarly, anisotite yield M equal to 5, S equal to 0.5 and C equal to 0, and diopside yield M equal to 0.25, S equal to 0.5 and C equal to 0.25, etc. The results are plotted on the diagram in figure, ignoring CO2 as mobile component. In order to understand projection in multiple dimension, it is easiest to begin with a simple example that we can see easily. We can simplify the diagram from a ternary 1 to pseudo-binary MgSi diagram, in which diopside is projected to a point at 33% Mg to Si 66%, as illustrated in figure. By performing the projection, we have managed to reduce the ternary system to a pseudo-binary one making it simpler. The ratio of MGO to SIO2 is in diapside is 1:2 or 33:67. So that we can plot diapside in a binary directly. So likewise, we can plot all the minerals in the ternary system or pseudo-binary. Like igneous rocks, metamorphic rocks are also composed of 9 or more major elements like SiO2, AL2O3, Fe2O3, FeO, MGO, MnO, CAO, Na2O, K2O and S2O. Thus, initially, it would appear that we are dealing with a 9 or 10 component system. However, the number of components in any given system is minimum number required to define the composition of all phases in the system. Thus, since constituents like Na2O and K2O are not usually found as separate mineral phases, we can combine these with other constituents like AL2O3 and SiO2 in the feldspar like albite and orthoclase, and thus reduce the number of components required to define our system Na2O plus K2O as alkali. This is important if we graphically display chemical, rock and mineral data in a way that is easily visualized. In fact, the best way to visualize such data is to attempt to reduce the number of components to 3 so that we can plot the composition of rock and minerals on a triangular composition diagram. Before discussing how this is done, we first review some of the principles of 3-component compositional diagram. Phase, that is distinct materials or state, plus degree of freedom independent variable equal to components plus 2, that is temperature and pressure. PS2O, PCO2, pH, oxygen phygosity and EH. Simplifying degree of freedom, generally we ignore pH, EH, oxygen phygosity for most rock. Important for sulfide system, usually care about pressure and temperature. Assume PS2 equal to P total for silicates, then PCO2 will be 0. Assume PCO2 equal to P total for carbonates, PS2 will be 0. Assume PS2 equal to 0 and PCO2 equal to 0 in some cases, then P plus F equal to C plus 2. If F equal to 2, then P equal to C. Number of phases equal to number of components. Component equal to SiO2, AL2O3, Fe2O3, FeO, CAO, MGO, Na2O, K2O, TiO2, Cr2O3, MnO, BaO, strontium oxide, P2O5, S2O, CO2, fluorine, chlorine, etc. Simplifying components, we can plot a maximum of 3 components using triangular diagrams. Ignore SiO2 axis, S2O axis or 0, CO2 axis or 0. Assume P2O5 goes into apatite, Na2O into albite, TiO2 into rutile or ilmenite, Cr2O3 into chromite, fluorine into fluoride or apatite, chlorine into halite. Include MnO with FeO, barium oxide and strontium oxide with calcium oxide, Fe2O3 with Al2O3 or FeO, chlorine, fluorine with OH. Subtract major element as necessary. Component reduced to Al2O3, FeO, MGO, K2O. AKF graph Al2O3, FeO plus MGO, K2O. Peltic sediments are high in AL2O3 and K2O and low in CAO. Ascola in 1915 proposed the AKF diagram as a way to illustrate metamorphic mineral assemblages on a simplified three-component triangular diagram. He concentrated only on the mineral that appeared or disappeared during metamorphism and also give idea about the grade of metamorphism. The chemical composition of rocks and silicate minerals is conventionally stated in terms of 10 main oxide, namely SIO2, AL2O3, Fe2O3, FeO, MGO, CAO, Na2O, K2O, MNO and S2O. It is impossible to represent graphically all possible variation in the mineralogy in a broad system of more than 3 or 4 components. Therefore, it is necessary to reduce the number of components for graphic representation. In common metamorphic rocks, SiO2 is present in excess. Quartz is mainly constitutes of many metamorphic rocks, and thus only those minerals with highest possible SiO2 content can be formed. Consequently, the amount of SiO2 has no influence on the mineral assemblages and thus need not be represented graphically. CAO is now subtracted from AL2O3 in calculating A, as with Na2O and K2O and their corresponding feldspar. This eliminates calcium oxide and plagioclase from the diagram also. Now we are interested only in the A that occurs in excess of that combined with potassium, sodium and calcium to make feldspar. As a result of this formulation, no plagioclase plot on the AKF diagram. Only one atom of calcium is subtracted from 2 of alumina because the Al ratio calcium is anorthite 2:1. S2O may be considered as mobile component and thus may not be considered. Similarly, Na2O and K2O may also be neglected because rocks containing alkali may have albite and potash feldspar as additional phases besides those shown in the diagram. As biotite and muscovite also contain K2O, therefore, a separate AKF used to represent the mineral assemblage and containing these micas. Thus, it is possible to reduce the components as follows: A equal to Al2O3 plus Fe2O3 because Fe thrice substitutes Al thrice. Second, FeO plus MGO plus MNO minus TiO2 if ilmenite is present. These can be combined together because MGO and MNO commonly substitutes FeO in silicate minerals. And third, K equal to K2O. On the basis of these considerations, Ascola neglected the minor component TiO2, P2O5 because they form accessory minerals, also neglected S2O and CO2 in view of their being mobile component. Na2O, which proxy other components, calcium in plagioclase, was also left out of consideration. Ascola reduced the remaining 7 components, namely Al2O3, Fe2O3, FeO, MGO, MNO, CAO, K2O into 3 components for his familiar known AKF diagram. Ascola in 1950 adopted the following reasons: since the bivalent cations Fe, Mg, Mn have similar ionic radii, they can be grouped as FeO plus MgO plus MNO as one component called F component. Assuming the substitution between the trivalent cations Al and Fe plus 3, Ascola combined Al2O3 plus Fe2O3 as one component and designated it as a component. Ascola gave equal importance to K2O, which served as the third component in this AKF diagram. The above three components are used by Ascola to present the mineral assemblages of metamorphic rocks of different phases. First, weight percentage of AL2O3, FeO, MGO, MNO, Fe2O3, CAO, K2O and Na2O are converted into molecular proportion by dividing weight percent oxide by the molecular weight of the oxide. Second, in albite, the molecular ratio Na2O ratio Al2O3 is 1:1. Similarly, in potash feldspar, the molecular ratio K2O ratio Al2O3 is also 1:1. Therefore, the molecular proportion of Na2O and K2O are added, Na2O plus K2O, and an equal amount to their sum is subtracted from the molecular proportion of Al2O3 plus Fe2O, that is Al2O3 plus Fe2O minus Na2O plus K2O plus CaO. Third, AKF can now be written as follows: A equal to Al2O3 plus Fe2O3 minus Na2O plus K2O plus CaO, K equal to K2O, F equal to FeO plus MGO plus MNO. For the purpose of graphic representation, these values are recalculated so that A plus F plus K equal to 100, that is, they are expressed as molecular percentage. The diagram is commonly used to represent the minor assemblages of peltic and quartzo-feldspathic rocks. A plus K plus F equal to 100, that is, in the molecular percentage, minerals whose composition is such that it contain only A and F component occupy the same position in the AKF diagram as in the ACF diagram. Calcium bearing minerals cannot be represented in AKF diagram. According to the calculation scheme, potash feldspar, microcline and orthoclase is plotted at the K corner in the diagram because an amount of Al2O3 equal to K2O, subtract KAlSi3O8, K2O ratio Al2O3 equal to 1:1. Muscovite of ideal composition K2O, 3Al2O3, 6SiO2, 2H2O is located at A equal to 67 and K equal to 33 because its K ratio A is 1:2 and amount of Al2O3 equal to 1 K2O has already been subtracted from the Al2O3 values. Biotite has a variable composition and is represented by a field. The ideal composition of biotite is K2O, 6 Mg Fe plus 2 MNO, bracket close, O, Al2O3, 6 SiO2, 2H2O. This composition points on the KF side of the diagram with 14 molecular percentage of K and 86 percentage F. In many biotite, however, FeMg is replaced by Al so that biotite is represented by a small field extending parallel to the AF side. K is approximately constant from the point of 14 percentage K, 86 percentage F. For example, biotite of composition K2O, 5 Mg FeO, 2 Al2O3, 6 SiO2, 2 H2O. Therefore, A equal to 14, K equal to 14 and F equal to 72. The AKF diagram has lost much of its usefulness since a better method is now available for the representation of FeMg and Al containing minerals which coexist with biotite and muscovite or potash feldspar. This method is AFM projection. The AKF diagram shows only the peltic and quartzo-feldspathic composition and their assemblages. The latter composition plot near the K corner of the diagram. The AKF diagram also useful as shows first the relationship of P with C of a rock system as a required by the phase rule. Second, compatibility of phase within a given rock composition. Third, the effect of bulk composition from those of metamorphic grade. AKF values of some common minerals, talc, Mg3, Si4O10 OH twice, A equal to 0, C equal to 0, F equal to 100%. Anthophyllite, cummingtonite, MgFe7, Si8, O22 OH twice, A equal to 0, C equal to 0, F equal to 100%. Hypersthene, MgFe twice, Si2O6, F equal to 100%. Pyrophyllite, AL2, Si4O10 OH twice, A equal to 100%. Kyanite, sillimanite, andalusite, AL2, SiO5, A equal to 100%. Staurolite, 2Al2O3, FeO, 2SiO2, S2O, A equal to 67 and F equal to 33 and K equal to 0. Chloritoid, FeO, Al2O3, SiO2, S2O, A equal to 50, F equal to 50 and K equal to 0. Almandine, Fe2, Al3, Si3O12, A equal to 25, F equal to 75 and K equal to 0. Cordierite, 2 MgFeO, 2 Al2O3, SiO2, F equal to 50 and A equal to 50. Chlorite, variable composition, F equal to 90 to 65 and A equal to 10 to 35. Mg5, MgAl, AlSi, Si3O10 OH8 up to MgFe4, Al2, Al2 Si2O10 OH8. Dear student, today in this lecture we have discussed about the AKF diagram. I believe this lecture was useful for you. In my next lecture, I will cover AFM projection. For further studies, please read the textbooks, references and links given in the text.